So good morning. Today I am here to explain the heat transfer in a bar. A totally conduction problems. So bar can be subjected to a various type of boundary conditions, means temperature boundary conditions, flux boundary conditions, or a combinations of the two. So this can be solved by MATLAB. So the generalized heat transfer in a rectangular coordinate is given by these equations. So this is heat transfer term in x direction, this is y direction, this is z directions. Okay, heat or generations means energy generated within the material per unit volume per unit time. Say energy accumulation within the material per unit volume per unit time. So to simplify this equations we have considered is a steady state heat transfer and no generation within the materials. So E dot generations and accumulation term, these two terms will vanish. So the equation 1 can be rewritten into these three energy terms in different directions. Further simplifications we have considered it totally is the heat transfer in x direction, so y and z term will vanish. So this equation it need to be solved now. For generally the conductivity is independent of temperature in medium temperature range, and we have also considered is independent of the space. So the k is constant, so it's taken out from here. So equation 3 can be rewritten as del square t upon del x square, and this can be rewritten into partial derivative can be converted into a total derivative. Since only one variable is involved, the variation is along the x direction only. So this can be written as d square t upon dx square. So second order differential equation that need to be solved using two boundary conditions. So this is a schematic of heat transfer in a bar. So the bar is of length L, and this is how we have given the nomenclature to this. So these are I equal to 1 to I equal to 2 and finally I equal to 1. So these are, you can say, the various difference points in the bar equally spaced, and we are trying to solve it by finite difference techniques using central difference formulations. The first case is that the temperature boundary conditions. So in temperature boundary conditions, temperature at the boundaries are known. So this is the temperature at left hand side of the boundary, this is the temperature at the right hand side of the boundary, and in between of that we have taken the n number of the difference point just to calculate the temperature at various positions within the materials. So this is simple forward difference central difference formula just to calculate the second order derivatives. So this is how Ti plus 1 minus 2 Ti plus I delta x square equal to 0. So this is, you can say, central difference formulations of this equation number 4. Now here for the space, the delta x is the point between two difference point distance, xl minus x0 for n. Now the delta x, for simplicity only convenience, we have considered as m. So we can rewrite equation this one as 1.1 equal to this into this particular coordinate. Now here the I can be changed from 1 to n, and so should get various equations. So if we substitute I equal to 1 into this one, so we will get this equation. So here T0 is known to us, this is the boundary temperature, where T1 and T2 are unknowns. So this equation can be rearranged into this one. So unknowns on the left hand side and knowns values are on the right hand side. Now we can change the I equal to 2. So we substitute I equal to 2, this is the resulting equation, then I equal to 3, the resulting equation, I equal to 4, then I equal to n minus 1, and then I equal to n. If you substitute here the last point at the end of the nth grid points, so we will get one more term tn plus 1. So this tn plus 1 is again the boundary, so it can be rewritten into this particular format. So these Tn minus 1 and Tn's are unknowns, and Tn plus is the boundary temperatures. So all these equations from S1.4 to 1.1 can be rearranged into the matrix format as following. So this is in matrix format. So this is first equation, then second, then third, and this is the second last. So if you observe is carefully in the matrix A1, so we give the nomenclature here A1 only for matrix A. Temperature coefficient of temperatures. So here you say here this have 2 terms. Rest this also have 3 terms. This is again 3 terms. This is 3, and last equation have 2 terms. So you see that it is a tridiagonal matrix, so whose elements are same. Only thing their positions is getting the shifted each time one to right hand side. So here you can say that this is a first position, now this is a second position, and the same thing will continue here, the third position, fourth position, fifth, and so on. Now this one here is boundary condition matrix. So this is the T0 is the temperature at the boundary, and left hand side Tn plus 1 the boundary temperature on the right hand side. Now these metrics need to be generated by any programming means language. So here I have used for MATLAB programming. So in that MATLAB programming, so these are few simple commands are what you use to generate the matrix. This is the commands that to generate the first row actually. So in this case we have here I equal to 1, so it's the first elements, second element of first row. So by giving this command, this is the second last element of last row, because these have same thing, same value, 1 upon m square, 1 upon m square. You can see from here this one and this one. Now the second commands to generate it, you can say that diagonal terms. So of diagonal terms you have one terms at I plus 1 and I minus 1, where I is always greater than equal to 2 or less than equal to n minus 1. So practically you are calculating this element and this element. Here this one and this one, this one, this one, this one, and this one. So these would be generated from this. Now only the diagonal term. So diagonal term is very easy. So it's can generated by this simple commands here, minus 2 by m square. So matrix A completely generated by these 3 commands, 1, 2, and 3. Now matrix B, that boundary condition, the matrix would be generated from this. This is the first element, this is the last elements, and finally once we have matrix we can calculate unknown temperature by A inverse multiplied by B. So this is the same way the program is being written for that. So these simple commands, and then you can have generated, and this is the analytical solution of that, which is also being plotted. So if you, this is the problem statement for this. So you have L was 0.2, thermal conductivity was 1.2 watt per meter per degree Celsius. Heat transfer area 15 meters square, and boundary temperature was 120 and 150 degrees Celsius. So this is the analytical expression for temperature solution is given by these expressions. Analytical heat transfer rate can be calculated by this only simplicity, and these are the calculated and analytical one temperature profile. So practically you said there are no visual difference from here, but if you calculated percentage error in temperature, so percentage wise you can say the total the highest error is nearly 0.025% actually. So that's not high percent. This percentage can be minimized further by taking the more and more difference point. But only thing your compression time will go up. So somehow we have to stop at some number of grades so that the error in temperature is acceptable. So this is all about your temperature boundary condition for heat transfer in a metal ball.